Okay, this chapter is about the following. Okay, you learned from one of the previous chapters that energy is conserved. You do not create energy or destroy energy. So the only two things you can do is transform energy from one form to another. Okay. So you can transform it and transfer it from one object to another. Okay, how do you transfer energy from this object to this object, let's say? So this could be you, and that's a Publix card or something like that. Okay. So the way you transfer energy is you do work. You apply a force and you do work on that object. Okay. How do you calculate the work done by a force? So you saw that. So the work done by a force is F dot displacement if the force is constant. Okay. And it's this integral if the force is changing and you're still going in a straight line. And this is how you calculate the work done if you're going in a general trajectory. It's a line integral. Okay. So for now, so this is 1D and this is 3D. All right, so this is how you calculate the work done. Now this entire chapter is the following. Okay. So what if the force is given by this function? So this entire chapter is based on the fundamental theorem of calculus, du by dx. Then the work done is du by dx, and you're going from this initial position to the final position. Again, this is the 1D case. Okay, so what does the fundamental theorem of calculus says? So this is du by dx. This is a derivative, and what is this guy called? Antiderivative. It undoes whatever this guy does. Okay, so integral of this is just u. Okay, and that's xi x. Okay, that's equal to u xf. Okay, so you see, calculating the work for such a force is very easy. Even your physics professor can do it. And you, of course, can do it much easier. Okay? This entire chapter is about that. Okay? Now, so we are going to put a minus sign because that's what's convenient. When it's a minus sign, this guy is called a potential energy function. We talked about gravitational potential energy already. Okay? This guy is called a conservative force. So this chapter is about forces that can be written like so. And what is great about them? Calculating the work. Is easy. Work done by such forces is negative ux final minus ux initial. It's that easy. Okay. And what is u?
The potential energy function.
Very good. Yep. And there are only 3 such forces. Okay. The 3 forces are gravity, the spring force, and the electrostatic force that we'll talk about, that you will learn about in in physics 2. So this semester, you're just learning these 2 forces. So here's an entire chapter dedicated to just these 2 forces. Okay. Friction is not it. You pushing on a cart is not it. Your car engine exerting a force is not it. There's a million forces that apply like that are not conservative forces. Elon Musk's rockets don't apply conservative forces. Yeah? So just these 3 forces are conservative forces. Okay? All right. So again, what is the neat thing about these forces? These forces are negative derivative of a potential energy function. Okay, and what does that do for us? Calculating work is very easy. And notice something about this. Okay, so when the object goes from this initial point to that final point, the work done is potential energy at the final point minus the potential energy at the initial point. How did you get there? Let's say you got there from there, or there, or like this. The work done by these forces is the same, is path independent. Yeah?
Why is it negative potential energy?
No, that's how it's defined.
Okay.
Okay. Did you guys understand that? Very simple chapter. And now I got 30 slides to confuse you. So you guys ready for that? All right.
So the U stands for potential energy.
U stands for potential energy. Okay. So let me ask you this. Is there a potential energy for the friction force? No. Is there a potential energy for Elon Musk's rockets?
No.
Is there a potential energy for you pushing on the Publix cart? No. All right. So we'll learn. We'll learn about potential energy for the gravitational force and for the spring force. And let me give it to you. Okay. So the potential energy for gravitational force, potential energy for gravity is mgh. Okay, so this is good for close to the surface of the Earth. Okay, this is good as long as g remains constant. Okay, you will learn as you go higher and higher up, g will decrease. Okay, so how far do you need to go up? You need to go up to distances comparable to the radius of the Earth. What is the radius of the Earth?
6,000 kilometers?
6,400 kilometers. Very good. 4,000 miles. So if you can jump up 1,000 miles, then you know g is changing. then you can't use this guy. Okay? So here's a more accurate expression for gravitational potential energy, but we'll wait till chapter 3 to learn about it. I mean, chapter 12, 13 to learn about it. Yep. So right now we'll be happy with this. And here's the spring potential energy. Yep. So remember we said that the forces are related to their potential energy function. So let's show you that. So the spring force is, what is it? Minus du by dx, right? So it's minus d by dx. What is the spring potential energy? Half kx squared. And derivative of x squared is what?
2x.
2x. So that cancels with that, so that becomes minus kx. And we know that that's the spring force. Okay? So this is a conservative force. Okay. Let's do that for gravity. So the force of gravity is minus d by, okay, so mgy, we are going to write it in terms of y is this coordinate. Okay, so it will be d by dy, and it's minus mg. Okay. So now if you want to do the force, then it's in terms of, okay, so the force of gravity is minus mg, j. It's in this direction. Okay. All right, so those are the only two forces that the conservative forces will deal with. Okay. So again, let me summarize this just so we are dealing with conservative forces. These forces can be written like so. This is the potential energy function, and this is in one dimension. Okay. Work done, easy to calculate. Work done is path independent. Work done is minus u final minus u initial. Okay. Okay, so that's the summary of the chapter. Okay. You guys understand this? And it's just using the fundamental theorem of calculus. What is it based on? This one simple equation. So this entire chapter is on this. Work done is integral of this force, and for the forces that we are considering, this integral is very easy to do because that force happens to be this, and from the fundamental theorem of calculus, see, this guy just undoes the integral, undoes the derivative. It's just the potential energy function evaluated at the endpoints. Yep. And that's the entire chapter. All right, do you guys have any questions before we get into the slides? Again.
One question.
Mhm.
Back on the potential.
I'm sorry?
Back on the slide with potential energy to gravity. Potential energy of gravity is meant.
Mm-hmm.
What's that supposed to be under mgh? Like, what are those supposed to be? Like,
This guy?
yeah.
So this is, this works close to the surface of the Earth, like within, let's say, 200 miles on the surface of the Earth. But if you go further than that, if h is bigger than that, then you have to use this formula, G is the gravitational constant. You will learn about this in chapter 13. M is the mass of the earth if you're jumping from earth, or it's the mass of whatever you're jumping from. This is your mass, and that's the distance measured from the center of the object. So if this is earth and this is you, that's R.
Alright, thank you.
Yeah. All right. So let's go over the slides. Again, I hope you're not confused, you don't get confused, but so we'll try and make it simple, okay? So when can you talk about potential energy? When you have conservative forces, okay? And there's only two that you will deal with, gravity and spring force, okay? And when only those conservative forces act, then mechanical energy is conserved. So when only conservative forces act, mechanical energy is kinetic energy plus potential energy, that is conserved. Okay? And that's what that title is about. Okay. So of course, if you take into account all forms of energy, that's always conserved. That's whether conservative forces act or non-conservative forces act, okay? So for instance, when I push a cart, if you account for energy in me and the cart, the total energy is always conserved, okay? We don't talk about that because that's hard to keep track of. There are some forms of energy that are hard to keep track of. Okay, so work and potential energy. So when you are dealing with conservative forces, work done by those forces can be tracked by keeping track of potential energy, yeah, and so on. So we'll talk about all this stuff. All right. So work done by a conservative force on a particle moving between 2 points is independent of the path. Okay? So this is what the definition of conservative forces in words, but you already know the mathematical meaning behind it. What is a conservative force? A force that can be given like so. And what was this part of the statement? Between 2 points is independent of the path. Well, work done by this force was given by this integral. And the fundamental theorem of calculus lets us evaluate this integral. It is just ux the value of the integral, which was the work done, depends only on the end points. It doesn't depend on the path taken. Okay? So for instance, when this guy is going down here, and if he ends up here, the work done by gravity doesn't depend on the shape of the track. And if there is no friction, his speed there will be independent of the shape of this track. That's what we're saying. Neat. Okay? Now, of course, so I need to be a little more careful. If you start off at rest, that has to be the highest point for you to get there. All right. So behind this statement is hidden all this math. Yeah. Friction is a non-conservative force, and if you're pushing this book along these paths, those are non-conservative force. And the work you do along this path will be different than the work done along this path. Okay? potential energy function. So if you have a conservative force, this guy is called the potential energy function. Okay? And there are only two potential energy functions you'll deal with. For gravity, we generally write it mgy. And for spring potential energy, what is the potential energy for the spring? 1/2 kx squared. Okay. All right, so you know what the potential energy function is. Okay. You guys understanding this? All right. Okay, so work done is defined as, so here is the conservative force, and you do that integral, it turns out to be the work done is change in potential energy function, negative of change in potential energy function. Change in any function is the function evaluated at the final point minus the function evaluated at the initial point. Okay? Okay. So potential energy can be defined when dealing with conservative forces, such as gravity, electrostatic, and spring forces. Yeah. Those are the only three forces. So here's a spring force. So let me illustrate what we mean by path independence here. Okay. So here's the spring force. Let's say the mass goes from here to there. You can calculate the work done by the spring force when the mass goes from here to there. Okay. X initial to X final. The work done by the spring force is minus 1/2 kx final square minus 1/2 kx initial square. Okay? And the work done is the same whether the mass went like this, the infinitely many paths it took to get there. Okay? See, the work done just depends on the initial and final points. It does not depend on the path taken. Okay? All right. So, no, this might look strange, but the work done is calculated like this, dx, initial to final point, and this is defined as change in potential energy. This is on 1D. And in 3D, this generalizes to a line integral. Okay? But, so now u is a three-dimensional function, okay? U is a function of x, y, and z. All right, so this shows you the derivation of the gravitational potential energy to be that, okay? So the work done by gravity is the gravitational force, and here is the displacement. Okay, so in this formula, your x-axis is this way, y-axis is this way. The gravitational force is minus mgj. J is a unit vector in this direction, and there is the small displacement along the y-axis. Okay. J dot j is 1. Okay. So the work done by gravity, and we are just doing for an up and down motion here, but dy, y initial to y final, minus mg y initial to y final. So here is the potential energy at the final point, here is the potential energy at the initial point. Okay? So there is the potential energy function. All right. And the same thing is done for the elastic, for the spring force. Here's the work done, there's the spring force, and you're integrating it over dx and x initial to x final, and this is what it works out to, and there is the spring potential energy. Okay. So there is the spring potential energy. Okay, I can't say this enough. The whole chapter is about, here's the work done by a general force. Okay? For a couple of forces, this integral is easy to do, that's all. Okay. And so it is associated with this function. You can associate a potential energy function, and that's the whole chapter. Okay?
Can you go back to the derivation for gravitational potential equation?
Okay, so there is the force of gravity,
Mm-hmm.
and there is the displacement.
Mm-hmm. And the vector, the j hats go to 1.
Mhm.
What about the y's? The y initial, y final underneath that.
Okay, so here is that derivation. So j dot j is, okay, so this is where we got that expression from. Okay?
Okay.
This was that, and dr was the displacement, the vector displacement. We are displacing it along the y-axis. J dot j is 1 minus mg dy.
Oh, okay.
That's a constant. You know.
Got it. Okay, thank you.
Yep. So you will see this conservation of mechanical energy. Mechanical energy is kinetic energy plus potential energy. Okay, that's. And this is conserved when only conservative forces act. So friction is not present, you're not pushing, there's no rockets involved, and so on. Okay? So this is true only when gravity and spring forces are in play. If there is any other forces in play, then you're out. Okay? You can have other forces that do not do work. Can you give me an example of a force that does not do work? Very good, my friend. Very good. If you ask me for a soda someday, maybe I might buy it for you. Okay? All right. So normal force does not do work. Okay? Okay. All right, so if you have a conservative force acting, then the work done by it is that. And if that's the only force acting, remember, we had a work energy theorem. The work done by all the forces just shows up as change in kinetic energy. Okay? Okay, so negative. So what we are saying is work done, the work done, you can calculate as change in potential energy, but that also shows up as change in kinetic energy. And so let's say the example is for gravity, and this change in potential energy is that, change in kinetic energy is that, and then you rearrange that. And so this is saying kinetic energy at the initial point plus potential energy at the initial point is equal to kinetic energy at the final point plus potential energy at the final point. Okay? So if this was your initial point, kinetic plus potential energy at this point is equal to kinetic plus potential energy at that point. Okay? And this need not be the final point. This could be the final point. This could be the final point. That's true at every location. The total energies conserved is the same value at all locations. Okay? And this is what we look in physics. So you'll see a complicated motion. Is there something that's constant? Okay? So now you just learned to say something powerful like that. So let's say you're designing a roller coaster. If it's a frictionless roller coaster, you start there, your speed will be the same no matter what the shape of the roller coaster is. Okay? And that's a pretty powerful statement. Yeah. So that's what this thing is about. Okay? All right. So when is mechanical energy conserved? Give me the technical answer. What needs to be absent?
Friction.
Non-conservative forces need to be absent. Okay? So only conservative forces are acting. I mean, we are using a hammer to kill a fly there, but you know. All right. So here's a picture. Okay, so there's the total energy, there's the mechanical energy, and this is potential energy, this is kinetic energy. As you go up, your kinetic energy is decreasing, you're slowing down, and then once your potential energy starts decreasing, your kinetic energy will increase. The sum of the two is constant. That's what the graph is showing you. Yeah. This is assuming there's no friction. All right, when non-conservative forces are present, what are these guys? Friction, pushing, rockets, etc., etc. So when non-conservative forces are present, you're changing the mechanical energy of the system. Okay, so in this statement, well, we're not going to keep track of the energy of the fuel in the rocket. We're just going to keep track of the energy of the rocket itself. Okay, so when non-conservative forces are present, they change the mechanical energy of your system. Okay, so if you do positive work, so if I'm pushing and I do positive work on that public's cart, I'm increasing the mechanical energy of the cart. Okay, that's what I'm saying. Look, friction is a non-conservative force. The thing about friction is the work done by friction is easy to calculate, very easy to calculate. Okay, which direction does friction act? Okay, by the way, so here's the general formula for work done by a constant force. Okay, so if here's an object and this object moves in that direction, which direction is friction acting? Opposite direction. Okay, and so the work done by friction is FD cosine 180, which is minus FD. Okay, so friction is a non-conservative force, but friction is sort of our friend in many situations, and since it's easy to calculate, we just separated it out. Okay. What does friction do?
Opposes motion.
Yeah, I know. And what is the end product?
Heat.
Heat. Very good. Okay. So, for instance, you brake your car. What happened to all the mechanical energy of your car? It was in the heat, got converted to the heat in the brake pads. Okay. So, when you're decreasing that much mechanical energy, you're increasing that much thermal energy. Okay, so the friction force generates that much thermal energy. Okay, so you bring that over to this side. So work done by non-conservative forces is change in mechanical energy and plus change in thermal energy. Okay, again, these are just bookkeeping devices. Don't worry about it. Okay, so for an isolated system where you can keep track of all the forms of energy, change in mechanical energy plus change in thermal energy plus change in internal energy is all zero, meaning total energy is conserved for an isolated system. Okay? Okay. So if there was no friction present, well, if there was friction present as well, if you could keep track of the heat and the mechanical energy, the total energy in this system would be the same at all locations. Okay? Now this is a higher level concept. You already know what the potential energy function is. Okay? For what forces can you give potential energy functions?
Conservative.
Yeah. Okay. And what are the two examples?
Gravity and spray force.
That's right. Okay. Okay. So if you can give a potential energy, so now we're making a general statement. If you can give a potential energy function for a system, then you can you have completely described the behavior of the system. Okay, so you can completely derive the behavior of a system. Okay, so there's a system here, and if you want to you want to describe the behavior of the system, all you have to do is throw the potential energy function in that guy. And then you can figure out how the system will behave. Okay, so here's a system. You can try and describe it or just throw this potential energy function at them. Okay, so what this does is you can calculate the force. So at this location, let's say the object is at this location, what is the force on it? You already know what the force is, minus du by dx, which is the slope of this tangent line. The slope of this tangent line is positive. Negative of that will give you a negative slope. And so that will be negative. So when the object is at this location, the force is in that direction. What is the magnitude of the force? It's the slope of the line. Okay? So if it's there, the force, the acceleration will be in that direction. Okay? So at that location, if it happened to be moving in this direction, you already know it's slowing down. It's accelerating in this direction. Okay? And if it's moving in that direction, it's speeding up, and so on. Okay? So the behavior of this system is contained entirely in that one function. And that's the point. Okay? So for instance, here's the potential energy curve. These are the turning points. Those are the turning points. At this point, the force is 0. When the two springs are not extended, the force is 0, and so on. Okay? So that's the power of this thing. Okay? So again, you guys understand? Given the potential energy function, you can completely determine the behavior of the system. Okay? So let me show you another potential. So let's say here's another potential energy function, whatever this is. Okay? Okay, so you can actually create this thing by putting a bead on a wire that's shaped like that. Here's the potential energy function for a marble on a hill. Okay? And you guys know this, so here's a marble there. That's an equilibrium position, but that's an unstable equilibrium. What does that mean? You disturb it slightly, you push it in this direction, it'll run away like that. You know that. But you can calculate it all. You push it in this direction, it'll run away like that. Here's a marble in a valley. Okay? You push it in this direction, it'll come back to that location. You push it in this direction, it'll come back to that location. This is called a stable equilibrium. Okay? So you disturb it from its equilibrium position. Forces that come into play are restoring it to your equilibrium position. In an unstable equilibrium, this is a local minima. Local minima of the potential energy functions are stable equilibrium points. Local maxima of potential energy functions are unstable equilibrium points. Okay, just terminology. But you guys understanding this? So this is the marriage of calculus and physics. Okay. So these are neutral equilibrium points. What are neutral equilibrium points? So you can put an object on a table, move it to a new location on the table, it'll still remain there. Okay? So neutral equilibrium points are a series of equilibrium points. So here is a potential energy function. This is for a diatomic molecule. Okay? What's a diatomic molecule?
Oxygen.
Oxygen. So you're surrounded by it. Oxygen and nitrogen are diatomic molecules. Okay, what this is giving you is, okay, the potential energy curve when these two molecules are that far apart. Okay, so the potential energy is, when they're this far apart, there's the potential energy. Okay, that's what it's giving you. Okay. Well, what good is this? You look at the potential energy function, okay, if the nitrogen molecules are this far apart, there's the potential energy. The force is minus du by dx. There is the slope of that tangent line. Negative of that, this molecule is being pulled in this direction. So if the two atoms were that far apart, this guy is being pulled. Where is the spot where it won't be pulled? So if it's this close, there's the slope. The slope is negative, and it's being pushed in this direction. When the atoms are this far apart, the force here is 0. Okay? And that's the equilibrium situation. Okay? So classically, that's the equilibrium situation. So there are about 10 to the power of 28 molecules here in this room. And you were smart enough that somebody gave you this graph, and instantly you knew that this was the intermolecular, that was the bond length. So that's what that graph told you. Do you guys understand? Okay. For all those molecules, that was the bond length. Now that's a classical statement. Quantum mechanics has something more to say, but we won't get there. We won't talk about that right now. I want to tell you one more thing. Do you guys have any questions at this point? I know that was a lot of information. Okay. Okay, so from what can you get the complete, what one thing can describe the behavior of the system completely for you? This one thing can describe the behavior of the system completely for you. Okay? So from the potential energy function, you can derive the behavior of the system completely. Okay? Yeah. All right, so again, you already saw that the force is negative derivative of the potential energy function. This is for 1D case. What does it generalize in the 3 dimensions? In 3 dimensions, force is a vector, is given by the negative of the gradient operator. The potential energy function is a scalar function, scalar valued function. All right. So now I want to make sure you understand the gradient operator. Have you guys seen the gradient operator? This is the gradient operator. Okay. Has anybody seen it? You've seen it. You're in Calc 3.
Yes, sir.
Okay. What does the gradient operator tell you? So in 3 dimensions, here's the force. The force is, and you can see that this is a generalization of the 1-dimensional case. Okay, there's the negative sign. Okay, and du by dx generalizes to the gradient. So what does the gradient operator tell you, my friend?
The gradient operator tells you that, in this instance, the force is equal to the sum of the partial derivatives of the potential energy function in each of the standard directions.
Okay,
So
so,
the partial
yeah.
derivative with respect to x in the I direction, the partial, plus the partial derivative with respect to y in the j direction, plus the partial with respect to z in the k direction.
All right, so here's what the gradient operator tells you. So you have u, x, y, z. This is your potential energy function, right? This is a scalar valued function. What does that mean? What does that mean? For every location, you associate a number. Okay, so let's say this is the potential energy function, and here its value is 100. Here it's 101. Here it's 102, 98, 97, and so on. Okay. So now you can ask the question, and this is a very legitimate question. You ask, in what direction is u increasing the fastest? Okay, let me write that down. In what direction is u increasing the fastest, and at what rate? And that's what the gradient operator gives you. Did you guys understand that? So if you evaluate the gradient operator at this location, and it gives you that it's increasing at 105 units per meter, that means that's given by this guy. This vector will be 105 meters per second in that direction. Okay? So the gradient operator tells you at what rate and in what direction it's increasing the fastest. And of course, all that this guy is telling you is the force is in the opposite direction. Okay? So the gradient is in that direction, this is the direction of the force. Okay, now we'll give it more meaning. Okay, so any questions so far? You guys understand that idea? Okay, so let me do an example. So let's say ux, y, z is equal to, we'll do a very simple example because I'm not very good at taking derivatives. Okay, so gradient of ux is del u by del x, partial derivative of u with respect to x, I, that's the x component, del u by del y j, plus del u by del z k. What does this guy mean? Del u by del x. What does it mean? What that means is the following. So if you're at this location, if you're at this location, how does u change if you move parallel to the x-axis? You can calculate that at any location. So del u by del x means how does u change as you move parallel to the x direction? Okay. If you're at this location, what does del u by del y tell you? The rate of change of u as you move in the y direction. Okay. What does del u by del z tell you? How does u change as you move in the z direction? Did you guys understand that? Okay. All right, so I'm not good at this. Help me out, my friend. What is del u by del x? U.
The rate of change of.
Yeah. So for this guy, what is del u by del x? Yep. So del u by del x means you treat all the other variables as constants. Okay? So this is equal to 2x y cubed z4. Okay? All right, my friend, Salzburg. All right,
Alright,
del u by del y. Have you been there to Salzburg?
no, I haven't.
Oh,
I just had to rep the shirt.
okay.
'Cause I'd like to go someday.
Yeah, so would I. Okay.
So this one would be, don't you just keep the?
So,
same-
yeah, the other variables are constant. You just take derivative with respect to
so
y.
it'd just be x squared, 3y z4.
Y squared is
Y
z4.
squared.
Yeah.
Okay.
Very good.
3x squared. Oh, never mind, I see what you did there.
Mhm.
Sorry.
Okay. And help me out with the last one. Okay, FSU.
X squared, y cubed, 4z cubed.
Yep, 4z cubed. Okay. So now you know how to take the partial derivatives and you know the meaning of it. Again, what does the gradient operator tell you?
It gives you the vector of the slope at that particular point.
So it's telling you the rate of fastest growth of that function. Okay? It's so notice this is a scalar valued function, and when you take the gradient operator, you're getting a vector out of it. Okay? And you need a vector because you need the direction of the fastest growth and you need the magnitude of the fastest growth. Okay? And that's what it's giving it. And forces are opposite, acting in the opposite direction. Okay? You guys understand?
So that's not displacement, it's just rate of change.
Yeah, derivatives are always rates of changes. Okay? Yeah. You guys understand? What was this chapter about? Forces that can be given as the derivative of the potential energy function. All right. I will see some of you guys, well, all of you guys in lab.